In this lesson, we will classify fluid flow in 5 useful ways. A single real flow can belong to one category in every pair. Watch the moving particles closely. Their speed, spacing, paths, and rotation reveal the classification. First, steady versus unsteady flow. At a fixed location in steady flow, properties such as velocity, pressure, and density do not change with time. Individual particles still move, but a velocity sensor at one point keeps reporting the same value. Water delivered through a pipeline at a constant operating condition is approximately steady. In unsteady flow, one or more properties at a location change with time. A valve opening, a pump starting, a reservoir draining, or a flood wave passing a bridge creates unsteady behavior. Notice how the particles alternately accelerate and slow down, while the observation point stays fixed. Second, uniform versus non-uniform flow. Uniformity compares different positions at the same instant. In uniform flow, the velocity is the same from one location to another along the direction being considered. The particle arrows have equal length. In non-uniform flow, velocity changes with position. Flow accelerating through a contracting pipe is non-uniform because the downstream particles move faster than the upstream particles. Flow near a channel transition, pipe entrance, or obstruction is also commonly non-uniform. This distinction is important. Steady describes change with time at a fixed point, while uniform describes change from point to point at one time. A flow can be steady but non-uniform, such as constant discharge through a fixed nozzle. Third, laminar versus turbulent flow. In laminar flow, fluid particles move in smooth layers with little mixing between neighboring paths. Dye injected into slow flow through a small tube stays as a distinct line. Viscous forces dominate and the motion is orderly. In turbulent flow, particles fluctuate in irregular directions. Twirls called eddies produce strong mixing and rapid momentum exchange. Most water flow in large civil engineering pipes, rivers, and spillways is turbulent. The main factors are velocity, a characteristic length such as pipe diameter, density, and viscosity. Their combined effect is often expressed through the Reynolds number. Fourth, incompressible versus compressible flow. In incompressible flow, the density of a moving fluid particle remains essentially constant. Water and other liquids are usually treated as incompressible under ordinary engineering conditions. Particle spacing stays nearly unchanged even when the pipe shape changes. In compressible flow, density can change significantly. Gases are compressible, especially when pressure changes are large or speeds approach the speed of sound. In the animation, the same mass occupies less volume as the particles pack more closely. At low speeds and modest pressure changes, even air can sometimes be approximated as incompressible. Fifth, rotational versus irrotational flow. Imagine marking a tiny fluid element with a short line. In rotational flow, the element spins about its own center as it travels. Flow in a forced vortex, like water driven around a stirred container, is rotational. In irrotational flow, a small element may translate and deform, but it has no net angular rotation about its own center. Curved particle paths do not automatically mean rotational flow. The deciding question is whether the fluid element itself spins. An ideal free vortex can follow circular paths, while remaining irrotational away from its center. Let us combine the classifications. Water moving at constant discharge through a contracting pipe can be steady, non-uniform, turbulent, incompressible, and locally rotational near the wall. Slow oil in a straight small tube may be steady, Uniform after the entrance region, laminar, incompressible, and largely irrotational near the center. Remember the visual clues. Steady or unsteady? Does a property at one point change with time? Uniform or non-uniform? Does it change from place to place? Laminar or turbulent? Are the pads orderly or strongly mixed? Incompressible or compressible? Does density remain constant? Rotational or irrotational? Does a small fluid element spin? Classifying the flow helps engineers choose the right equations and assumptions for analysis.